Hello everyone! In this video we will explore the foundations of the 12-factor methodology and understand how it shapes modern cloud-native architecture and production-ready systems. So here is what we will cover in this lesson. First, we will begin by understanding why the 12-factor methodology still matters. We will clarify its relevance and set the conceptual foundation for everything that follows. Then I will explain who this course is designed for, whether you are a developer, architect, or DevOps engineer, and why these principles are critical for each of these roles. Next, we will examine the systemic problems that 12-factor eliminates in modern distributed systems. From there, we will connect these ideas to cloud platforms, Kubernetes, and SaaS operating models, so you clearly see how application architecture aligns with infrastructure and business expectations. After establishing the modern context, we will step back into history. We will explore the origin of 12-factor at Heroku, discuss the deployment challenges that existed before the cloud era, and analyze the architectural shift from monolithic systems to cloud-native design. You will also understand why past platforms required architectural standards in the first place. Then, we will follow the evolution of 12-factor principles into the Kubernetes era and see how they adapted and remained relevant as the ecosystem matured. Once the context is clear, we will move into structure. I will provide a high-level walkthrough of all 12 factors, show you how they can be logically grouped by concern, and explain the importance of separating build, release, and run responsibilities. After that, we will analyze how the factors reinforce each other as a system, rather than as isolated rules. Finally, we will conclude by discussing how to apply 12-factor thinking in real production environments, so you can translate theory into practice. So by the end of this lesson, you will not only understand what the 12 factors are, but why they exist, how they evolved, and how they shape modern software architecture. When we speak about the 12-factor methodology, we are not speaking about a trend, a framework, or a tool. We are speaking about a set of architectural principles that address fundamental problems of software delivery. And those problems have not disappeared. In fact, they have intensified. Modern systems are distributed. They run in containers. They scale dynamically. They integrate with dozens of external services. They are deployed multiple times per day. Under these conditions, accidental complexity grows extremely fast. Configuration leaks into code, environments drift apart, deployments become fragile, scaling becomes unpredictable, recovery becomes slow. The 12-factor approach remains relevant because it attacks these issues at their root. It enforces strict separation between code and configuration. It treats backend services as replaceable resources rather than tightly coupled infrastructure. It demands stateless processes, which makes horizontal scaling not only possible, but natural. It formalizes the separation of build, release, and run stages, reducing ambiguity and deployment risk. These are not fashionable ideas. They are structural safeguards. Even when technologies evolve, the constraints of distributed systems do not change. A container is still a process. A cloud platform is still an execution environment. A Kubernetes cluster still runs applications that must start fast, stop cleanly, and scale safely. The operational physics remain the same. What 12-factor provides is a mental model. It gives teams a common language for discussing production readiness. It creates architectural discipline in environments that otherwise drift towards chaos. Without such discipline, systems become environment-dependent, deployment-dependent, and person-dependent. In other words, 12-factor matters because it transforms software from something that merely runs into something that can reliably operate. And reliability, scalability, and maintainability are not temporary concerns. They are permanent characteristics of serious software systems. This course is designed for professionals who are directly responsible for how software behaves in the real world, not just how it compiles on a laptop. First, it is for developers, not only senior engineers, but anyone who writes production code. If you are building web services, APIs, microservices, or SaaS platforms, you are already making architectural decisions whether you realize it or not. The way you handle configuration, the way you manage dependencies, the way your application starts and shuts down, these choices determine whether your system scales cleanly or collapses under pressure. This course gives developers a production-oriented mindset, so they stop thinking only about features and start thinking about operability. Second, this course is for software architects. Architects define boundaries, service granularity, infrastructure contracts, and deployment models. The 12-factor principles provide a structural foundation for those decisions. Without such a foundation, architectures tend to become theoretical diagrams disconnected from operational reality. Here we connect architectural thinking directly to runtime behavior, scalability, and long-term maintainability. Third, it is for DevOps engineers and platform engineers. These professionals live at the intersection of infrastructure and application design. They deal with CI pipelines, container orchestration, environment management, logging systems, scaling policies, and production incidents. The 12-factor methodology gives DevOps a consistent contract with development teams. It clarifies expectations, it reduces friction, it standardizes how applications should behave inside modern platforms. Ultimately, this course is for anyone who understands that writing code is only part of the job. Real software must be deployable, scalable, observable, and resilient. If you're involved in building or operating systems that must survive in production, this course is for you. When we examine modern distributed systems, we quickly notice that most failures are not caused by algorithms. They are caused by systemic weaknesses. The problems are architectural, operational, and organizational. The 12-factor methodology was created precisely to eliminate these systemic weaknesses. One of the most common problems is configuration chaos. Applications behave differently across environments because configuration is mixed with code, hard-coded in files, or manually modified on servers. As a result, development, staging, and production drift apart. The 12-factor principle of strict config separation removes this instability. It forces configuration into the environment, making deployments consistent and predictable. Another systemic issue is tight coupling to infrastructure. Applications often assume a specific database, a specific message broker, or a specific file system layout. When infrastructure changes, the application breaks. By treating backend services as attached resources, 12-factor eliminates this rigidity. Services become replaceable, migration becomes possible, vendor lock becomes weaker. Statefulness is another major structural flaw. When processes store session data in memory or write temporary files locally, horizontal scaling becomes difficult or impossible. Recovery becomes slow because instances cannot be terminated safely. The stateless process model removes this bottleneck. It allows instances to scale out, restart quickly, and recover without complex coordination. Deployment fragility is also a systemic problem. When build, release, and run stages are blurred together, teams lose control over what exactly is running in production. Hotfixes are applied directly to servers. Reproducibility disappears. The separation of build, release, and run introduces clarity and traceability. Every deployment becomes intentional and reversible. Finally, there is the problem of operational invisibility. Applications that do not treat logs as event streams or that depend on local files for monitoring become opaque in distributed environments. 12-factor promotes stream-based logging, which enables centralized aggregation and observability across instances. In essence, 12-factor does not solve isolated technical issues. It eliminates structural instability. It reduces hidden coupling. It enforces environmental consistency. It makes systems replaceable, scalable, and observable by design. And in distributed architectures, systemic stability is far more important than local optimization. Now let us look at this diagram together. At the very top, you see the 12-factor application principles. This is the foundation. This layer represents how the application itself is designed and built. Not the infrastructure, not the platform, the code, the structure, the operational assumptions embedded directly into the system. Now move your attention to the middle layer. Here we have cloud platforms and Kubernetes. These technologies provide dynamic infrastructure and orchestration. They allocate resources automatically. They restart failed instances. They scale replicas. They route traffic. However, and this is critical, they do not fix architectural mistakes inside your application. Cloud infrastructure assumes that instances can appear and disappear at any time. Kubernetes assumes that containers are disposable processes that bind to a port, respond to health checks, and can be replicated horizontally. If your application stores state locally, relies on manual configuration, or cannot start and stop cleanly, the platform cannot save you. It will only amplify the instability. This is where the alignment becomes visible. The 12-factor principles prepare the application to live inside this environment. Stateless processes allow horizontal scaling. Externalized configuration enables clean deployment across environments. Log streaming enables centralized observability. Clear separation between build and run makes automated pipelines reliable. Now look at the bottom layer of the diagram, the SaaS business model. SaaS is not just a technical deployment choice, it is an operational commitment. Continuous delivery, multi-environment setups, unpredictable load, and strict reliability requirements are business expectations. Revenue depends on uptime. Customer trust depends on consistency. Cloud gives elasticity. Kubernetes gives orchestration. But SaaS demands operational discipline. And that discipline starts at the application level. So the direction of the diagram matters. The 12-factor layer supports cloud-native architecture. Cloud-native architecture enables dynamic and automated infrastructure. And that infrastructure makes the SaaS model economically and technically viable. If the top layer is weak, everything above it becomes fragile. If the foundation is correct, the entire stack becomes predictable. This is why 12-factor is not just a checklist. It is the architectural contract between your code and the modern operational world. To understand the origin of the 12-factor methodology, we need to step back into the early days of platform as a service. At that time, many teams were still deploying applications manually, servers were configured by hand, environments were inconsistent. Scaling required careful coordination and often downtime. The operational burden was heavy. It was within this context that 12-factor emerged at Heroku. Heroku was building one of the early platform-as-a-service offerings, and their goal was ambitious. They wanted developers to focus on writing code while the platform handled deployment, scaling, and infrastructure management. However, they quickly discovered something important. The platform could only automate what the application allowed it to automate. Applications were arriving with hard-coded configuration, hidden dependencies, local file storage assumptions, and tightly coupled services. Each of these characteristics made automation difficult or impossible. The platform could not reliably scale or redeploy applications that were not designed for such behavior. As a result, the 12-factor methodology was not invented as theory. It was extracted from operational experience. It was a response to recurrent deployment failures and architectural friction. The team at Heroku began formalizing the characteristics that made applications behave predictably inside a dynamic platform environment. In other words, 12-factor was born out of practical necessity. It defined how applications should be structured if they were to live successfully on a managed cloud platform. Over time, these principles proved to be broadly applicable, not only to one provider, but to distributed systems in general. So the origin of 12-factor is deeply operational. It is rooted in the challenge of making software deployable, scalable, and manageable in automated environments. And that practical foundation is one of the reasons the methodology has endured. Before the cloud era, deployment was a fundamentally different activity. It was not continuous, it was not automated, and most importantly, it was not designed for change. Applications were typically deployed onto long-living physical servers or virtual machines that were manually configured. Each server often had a slightly different setup. Library versions differed. Environment variables were inconsistent. Sometimes configuration lived directly inside the source code. As a result, the phrase "it works on my machine" was not a joke. It was a structural problem. Because infrastructure was relatively static, scaling was slow and expensive. If traffic increased, you could not simply replicate instances in seconds. You had to provision hardware, configure it manually, and integrate it into the existing system. This meant that many applications were designed with vertical scaling in mind, relying on bigger machines rather than more machines. Consequently, architecture decisions were constrained by hardware limitations. Another major issue was release management. Build, configuration, and runtime were often mixed together. A deployment might involve copying files via FTP, running manual scripts on the production server, and modifying configuration directly on the machine. If something failed, rollback was complicated because there was no clean separation between versions. Production environments became snowflakes, unique, fragile, and difficult to reproduce. Furthermore, operational visibility was limited. Logs were written to local files. Monitoring was minimal. If a process crashed, recovery frequently required manual intervention. High availability was expensive and complex, so many systems simply accepted downtime as normal. In such an environment, consistency was rare. Automation was limited, and deployment carried significant risk. These challenges created the need for a new mindset. As we discussed earlier when examining modern platforms, dynamic environments require predictable application behavior. The deployment pain of the pre-cloud era exposed exactly what was missing: architectural discipline that supports automation, reproducibility, and scalability by design. For many years, monolithic architecture was the default approach to building software systems. A single codebase contained all business logic, all modules were tightly integrated, and the application was deployed as one large unit. This model was not irrational. It matched the infrastructure of its time. Servers were stable, scaling was limited, and deployment cycles were relatively infrequent. However, monolithic systems tend to accumulate internal coupling. Components depend on shared memory, shared databases, and shared deployment processes. As the system grows, even small changes require rebuilding and redeploying the entire application. Over time, release cycles slow down. Testing becomes heavier. Risk increases with every modification. Now contrast this with the shift toward cloud-native architecture. Instead of building one large unit, systems are decomposed into smaller, independently deployable services. Each service owns its boundaries, communicates over the network, and can scale independently. Infrastructure is dynamic rather than static. Instances are expected to be disposable. Automation replaces manual coordination. This shift was not purely about technology. It was driven by operational demands. Organizations needed faster release cycles, higher availability, and the ability to respond quickly to changing load patterns. A tightly coupled monolith struggles in such an environment because its deployment unit is too large and its internal state is too intertwined. Cloud-native architecture embraces isolation, statelessness, and horizontal scalability. As we discussed before when examining distributed environments, scalability and resilience require processes that can be replicated and restarted without side effects. This is much harder to achieve in a traditional monolithic system where state and logic are deeply interconnected. That does not mean monoliths are inherently wrong. They can be efficient and simpler in certain contexts. However, when operating in dynamic infrastructure with continuous delivery expectations, the architectural assumptions must change. The cloud-native shift reflects this reality. It represents a movement from tightly bound systems optimized for stability to loosely coupled systems optimized for adaptability. Understanding this transition is essential because 12-factor principles were designed precisely to support this new architectural landscape. When Platform as a Service first appeared, its promise was simple and powerful. Developers would push their code, and the platform would handle everything else: provisioning, scaling, routing, and recovery. However, very quickly providers discovered a fundamental limitation. Automation only works when the system being automated behaves predictably. Applications were arriving with implicit assumptions. Some depended on specific file system layouts, others stored session data in local memory. Many required manual configuration changes on the server. From the platform's perspective, each application behaved differently. That variability made large-scale automation nearly impossible. As we discussed earlier when looking at deployment challenges, inconsistency is the enemy of reliability. A platform cannot reliably scale an application if the application keeps state locally. It cannot safely restart instances if startup time is unpredictable. It cannot perform automated deployments if build and runtime responsibilities are mixed together. Therefore, PaaS platforms required architectural standards not for philosophical reasons, but for operational survival. They needed a contract between the application and the platform. That contract defined expectations. Configuration must be externalized, processes must be stateless, services must be attachable resources, logs must be streamable. With these constraints in place, automation becomes feasible. Architectural standards also reduce friction between teams. When every application follows the same structural rules, tooling can be standardized. Deployment pipelines become reusable. Monitoring becomes consistent. Operational procedures become repeatable. Without standards, every new service introduces new exceptions and the platform becomes fragile. In essence, PaaS required architectural discipline because abstraction alone was not enough. Infrastructure can be abstracted, but application behavior must align with that abstraction. The need for standardization was a direct consequence of attempting to automate software delivery at scale. And from that need, formal principles such as 12-factor naturally emerged.